An application to physics and engineering, moments and centers of mass. Our main objective in this section is to find a point, P, on which a thin plate of any given shape will balance horizontally. This point is called the center of mass of the plate. We're going to start with a simplest case and work our way up to more complicated cases. The simplest case says, well, if we just have two masses that are on opposite sides of a fulcrum, they're attached to a rod, and they're at distances d1 and d2 from the fulcrum, the rod will balance if m1 d1 is equal to m2 d2. And this is called the law of the lever. So now what we're going to do is we're going to try and generalize this. We're going to say, well, what if we have a bunch of different masses at different distances from this fulcrum? So we make the assumption that there will be a center of mass to place the fulcrum, and we'll call that center of mass x bar. And then we have the endpoints. We're going to call them x1 and x2, and more generally we'll have x3 and x up through xn. These numbers, these products of m1, the mass, x1, the distance from the fulcrum, are called the moments of the system. Now, in general, if we have a system of n particles with masses m1 through mn located at points x1 through xn on the x-axis, it can be shown that the center of mass of the system is located at x bar is equal to the sum of the moments, the sum of the individual moments, divided by the sum of the masses. And the sum of the individual moments, which is the numerator of that expression, that's called the moment of the system about the origin. Now, this moment of the system about the origin, if we consider that phrase, that is the moment, that's the tendency to rotate about the origin. And we'll see what we mean by that in a moment. So let's consider this example. We have point masses located on the x-axis as shown. We're asked to find the moment m of the system about the origin and the center of mass. Alright, so to find the moment of the system, the moment would be the sum from I equals 1 to 3. Since there are 3 point masses, we would have our sum going from 1 to 3 of mi xi. Alright, so recall what that means from your sigma notation. That means we would have m1 times x1 plus m2 times x2 plus m3 times x3. Substituting, m1 is 12, x1 is negative 3, plus m2 is 15, x2 is 2, plus m3 is 20, by x3 is 8. Simplifying gives negative 36 plus 30 plus 160, which is 154. So the moment of the system about the origin is 154. What that means is, if I were to place the fulcrum at 0, right? So if I was to place the fulcrum at the origin, since the moment is positive, the number line would in a sense tilt to the positive side. There's too much weight on the positive side of the origin, and so it would tilt to that side. It would not balance. We want to find the center of mass. All right, so if the moment is 154, then the center of mass, x bar, is the moment divided by the sum of the individual masses from 1 to 3. And so then the moment, so then x bar, would be the moment, which is 154, divided by the sum of the masses. Well, the masses are 12, 15, and 20. And so that's 154 over 47, which is approximately 3.28. So what that means is, to balance this system, I would want to place the fulcrum right about there. There's 3.28, approximately. If I were to place the fulcrum right there, then the rod would balance perfectly. So that was the one-dimensional case on the number line. And now we can consider a two-dimensional case. So now what if we have particles, n particles, with masses m1 through mn located at points x1, y1 through xn, yn on the xy plane. And so now our idea extends a little bit further. So now we have to not just consider a position on the x-axis, but also a position on the y-axis in which to place the fulcrum to balance a plate, in a sense. Okay, so by analogy, we will define the moment of the system about the y-axis to be m sub y, and m sub y is given by sigma from 1 to n of mixi. So notice, the moment about the y-axis, we find the moments with the x-coordinate, because the moment about the y-axis is the tendency to rotate about the y-axis. And so if we think, okay, well, if we're rotating about the y-axis, which again I've just drawn here in purple, if you sort of think about where the y-axis sits, you want to think about the x-coordinates, because the x-coordinates rotate about the y-axis in a sense. And similarly, the moment about the x-axis, we consider the y-coordinates, because the moment of the system about the x-axis is the tendency to rotate about the x-axis. And so if we just sort of think, okay, well, there's my x-axis, I need to consider the y-coordinates to see if it's too heavy above or too heavy below the y-axis. I'm sorry, the x-axis. All right, so the moment of the system about the y-axis, m sub y, is the sum of the products of the masses times the x-coordinates. And the moment of the system about the x-axis, m sub x, is the sum of the masses times the y-coordinates. So we can find those individual moments about the y-axis and x-axis, and we can find the x-coordinate, the x-center and the y-center by taking the moment, so the x-center is m sub y divided by the sum of the masses, and the y-center is m sub x divided by the sum of the masses. And we call the centroid is the center of mass and is given by the ordered pair x bar, y bar. So let's consider an example here. We have 4 masses of weights 5, 4, 3, and 6 at respective points -4, 2, 0, 5, 3, 2, and 1, -2. Find the moments of the system and the center of mass of the system. I'll start by finding m sub y, the moment of the system about the y-axis. So m sub y, recall, would be sigma from I equals 1 to 4 of m sub I, x sub I. So that would be 5 times x sub 1 is -4, plus 4 times x sub 2 is 0, plus 3, x sub 3 is 3, plus 6, x sub 1 is 1. I'm sorry, x sub 4 is 1. Alright, so if we add that up, let's see, that's -20 plus 0 plus 9, that's -11 plus 6 is -5. M sub y is -5. So what that means is the weight, there's more weight to the left, right? It's weighted more to the left of the y-axis than to the right. And so if you were to think of the y-axis as being held steady, the plane would rotate left of the y-axis. Similarly, let's find m sub x. And so that would be sigma I equals 1 to 4 of m sub I, y sub I. And so that would be 5 times 2 plus 4 times 5 plus 3 times 2 plus 6 times -2. So let's see, that's 10 plus 20, that's 30, plus 6 is 36, plus -12, which is 24. Alright, so now what that means is if m sub x, the moment about the x-axis, is 24, that means that if we were to think of the x-axis as being held steady, there's too much weight above the x-axis and it would rotate in that direction. So there's the individual moments of the system, or I should say the moment about the y-axis and the moment about the x-axis. The sum of the masses, well, that would be sigma I equals 1 to 4 of m sub I, which is 5 plus 4 plus 3 plus 6, and that's 18. So then x bar is m sub y over m, which is -5 over 18, or -5/18. Y bar would be m sub x over m, which is 24 over 18, which reduces to 4/3. So then the centroid, the center of mass of this system, would be the ordered pair -5/18, 4/3. That means is if I were to place a fulcrum underneath the plane at that point, it would be perfectly balanced. In our previous examples, we were just considering points, either on one dimension or in 2 dimensions. But what if we had, instead of just points, a thin plate, which is often called a lamina, with a uniform density rho, that's a Greek symbol rho, that occupies some region R in the plane. The center of mass of that plate is called the centroid. It can be shown that the centroid of the region R with area A is given by the points x bar is equal to 1 over a times the integral from a to b of x f of x dx, and y bar is equal to 1 over a integral a to b of 1/2 of f of x squared dx. A proof of these statements is available in your textbook. So, for example, find the centroid of the region bounded by y equals the square root of x, y equals 0, and x equals 4. Let's get a quick sketch of this. So let's see, y equals the square root of x looks like this. Let's say here's x equals 4. And y equals 0, of course, is the x-axis. So the region we're talking about looks like this. Right? There's the region. Now, just sort of looking at this, it appears to be, if we consider that region, it appears to be a little bottom-heavy and a little right-heavy. So I expect the centroid, since this is we're assuming it's a uniform density plate, I would assume that the centroid would be a little bit to the right. It would be right of the center of the geometric center of this region. It would be right of the center and below the center. And so what I mean by that is if we just sort of consider, this rectangle, it appears to be right heavy and bottom heavy. I am expecting the center to be somewhere over here. Okay, not necessarily the dead center of the actual geometric figure, just to the right and below, because that's where it's mostly weighted. That's where I would need to put the fulcrum to balance it. Alright, so considering what we saw in the previous slide, we know we're going to need to find the area of that region, and that's a Calculus 1 exercise. The area would be the integral from 0 to 4 of the square root of x dx, which evaluates as 16/3. Alright, so x bar would be 1 over a, so 1 over 16/3, times the integral from 0 to 4 of x times the function, so x times the square root of x dx. This is a Calculus 1 integral, and so this becomes 3/16 times, right, because 1 divided by 16/3 is 3/16. The integral itself evaluates as 64/5, and that simplifies as 12/5 or 2.4. Y bar would be 1 over a, so 1 over 16/3, and again, integral from 0 to 4, and now we would have a 1/2 f of x squared, so 1/2 square root of x squared dx. And so again, this is a Calculus 1 integral. We'd have 3/16 times the 1/2, and from the integral from 0 to 4 of the square root of x squared, that would give you 8 exactly, and this simplifies as 12 over 16 or 0.75. And so then the centroid would be 2.4, 0.75. If instead we have a region that lies between two curves, f of x and g of x, where we make the assumption that f of x is greater than or equal to g of x, then the centroid is given by x bar is equal to 1 divided by a times the integral from a to b of x times the difference of f of x and g of x dx. And y bar is given as 1 over a times the integral of a to b of 1/2 times the quantity f of x squared minus g of x squared dx. So notice it's quite similar, just have to adjust our thinking a little bit. So let's find the centroid of the region bounded by y equals 2 minus x squared and y equals x. Again, what I'll do is draw a rough sketch. 2 minus x squared is a parabola opening down, vertex at 0, 2. So it looks roughly like this. And y equals x is a line. It looks roughly like this. So here's the region we're concerned about. We need to find where they intersect, and since they're both written in the form y equals, they're both in function form, I can just set them equal to each other and solve the equation simultaneously. So this becomes x squared plus x minus 2 is 0, which factors as x plus 2 by x minus 1. So x equals negative 2 and x equals 1. So I'll first find the area. That would be the integral from negative 2 to 1 of the upper function minus the lower function. So the upper function, that would be what? 2 minus x squared minus x dx. Again, this is a calculus 1 integral and evaluates as 9/2. X bar would be 1 over 9/2 times the integral from negative 2 to 1 of x times the upper function minus the lower function. So 2 minus x squared minus x dx. Evaluating this integral either through symbolic techniques or a calculator, this is a calculus 1 integral, and multiplying it by the reciprocal of 9/2, you should find this to be negative 1/2. Y bar would be 1 over 9/2 times the integral from negative 2 to 1 of 1/2 times the upper function square minus the lower function square dx. And again, evaluating this integral and multiplying it by 1 over 9/2, you would get 2/5. So then the centroid is negative 1/2, 2/5. All right, that concludes this presentation.